Let G be a group and let A be a member of G. Notice that G is not assumed to be cyclic. A is an element. We can, in any group, whether the group is cyclic or not, consider the cyclic subgroup generated by an element. We can always do that. And that's what we're doing here. If that element A happens to have infinite order, the conclusion is that A to the I equals A to the J if and only if I equals J. Said another way, if I is different than J, think about the contrapositive of this statement. If I is different than J, then A to the I and A to the J will be different. That happens when your element has infinite order, like any non-zero element of Z does. On the other hand, the part we're more interested in here, if A has finite order, say order n, then the cyclic subgroup generated by A consists of all powers of A. Yes, it does consist of all powers of A, but they can be simplified to just these powers of A, E being A to the 0 power, then A to the first, A squared, etc., up through A to the n minus 1 power. And also, we've got an if and only if statement in addition to that. A to the I equals A to the J if and only if n divides I minus J, where again, n is the order of A. So let's try to work through the idea of the proof of this. And I want you, in working through this, I want you to believe, I want you to come to the point where you believe you could prove this if you had to, from scratch on your own. Again, probably not a full proof on the test because it would be too long, but maybe part of the proof on the test. So let's think first of all about if A has order n, why does that imply that the cyclic subgroup generated by A can be written as E, A to the 0 power, A to the first power, A squared through A to the n minus 1. Why is that true? We're essentially going to be doing scratch work for the proof. Or you could call it the idea of the proof. What are we trying to show here? We're trying to show an equality between two sets, a set equality. So the question becomes, how do you show two sets are equal? It's a two-step process. You got two sets in general, A and B. You're trying to show they're equal. First step is to show A is a subset of B. Second step is to show B is a subset of A. Two-step process. But how do you do that? How do you show something as a subset of something else? A is a subset of B if and only if, think about it intuitively, you could draw a picture here. If and only if A is inside of B, but what does that mean? It means if and only if any element of A must also be an element of B. If and only if the implication X being an A implies X is in B is true. That's what it means to be a subset. So coming back to the problem at hand, we wanted to show these two sets are equal, show this is a subset of that, and also this is a subset of that. One of those inclusions is trivial. Every element of here certainly is an element of that, right? Because by definition, this symbol represents the set of all powers of A. Hey, these are all powers of A. Any one of these n elements must be in there. I'll just say that inclusion is trivial by definition of the cyclic subgroup generated by A. The only thing where you have to do any work really is this inclusion. right? What is again the definition of the cyclic subgroup generated by A? It's the set of all powers of A. And remember, yes, that's how we define it as a set, but we did also prove it was a subgroup with one of the subgroup tests. That's what it is by definition. So I have to take an arbitrary element of here, of this set, and show it's one of these elements. How do we do that for examples? Think about how you do that for examples. Take even abstract examples. Take the case where, like we thought about before, the order of A is 6. What do we do for examples? Like, how do we figure out what A to the 7th is? Well, that's A to the 6 times A. And we know since A has order 6, that A to the 6 is E. A to the 7th simplifies to A. How do we do it for, say, A to the 15th? We got to relate it to A to the 6th. This is A to the 6th times A to the 6th times A to the 3rd. E times A cubed, that simplifies to A cubed. What are we doing here? We're really using properties of exponents, along with the fact that, say, with the 15, we can think of it as 6 plus 6 plus 3, or in other words, we can think of 15 as 2 times 6 plus 3. Does that feel familiar? That should remind you the equality of 15 with 2 times 6 plus 3 of the division algorithm. In particular, when we divide 15 by 6, we get a quotient of 2 and a remainder of 3. And by thinking about examples like that, that provides the inspiration, we hope, for the rest of this proof. Give me an arbitrary power of A, an arbitrary element of the cyclic subgroup generated by A. How do I show it's an element in here? How do I figure out which element it is, so to speak? If K were 15, the answer is it's A cubed. How do you figure that out? Use the division algorithm. The division algorithm from chapter 0 is super useful. The division algorithm is going to imply the existence uniquely, a unique existence of integers Q and R such that K, the power is, we're dividing by n, Q times n plus R, where the remainder, we talked about this before, is between 0 and what you're dividing by n, possibly equal to 0, but not equal to what you're dividing by. The uniqueness is with respect to that condition. You can come up with other equations involving other Q's and other R's where this is true, but there's a unique Q and R that also satisfies this condition. And so use it. A to the K is then going to be A to the Q times N plus R. Do the same kind of thing we did over here for this example. Use properties of exponents, first of all. And then use the fact that A is assumed to have order n. That was the original assumption. A has order n. That A to the Qn is going to be E. How do you rigorously show that? It's a property of exponents. Rewrite the A to the Qn as A to the n to the Q. That's a property of exponents. A to the n is E because the order of A is n. E to the Q is E. E times A to the R is A to the R. So, just like happened with the example, A to the given power is equal to A to the remainder that I get when I divide that original power by the order of A. R is in here. That's important. That means R is either 0 or 1 or 2 or 3, etc., through n minus 1. In other words, a to the k is one of these elements. So the next thing we're thinking about proving here is that a to the I equals a to the j, if and only if n, the order of a, divides I minus j. We're still in a situation where the order of a is assumed to be equal to n. This is not about set inclusions. This is about numbers, effectively, the relationship between I, n, and j, as well as the group element a. But it is an if and only if, IFF. So to prove it, we need to prove two directions. The easier direction is the backwards direction. Let's try that first. Again, essentially, we're just doing the scratch work here. The idea of the proof is what we're trying to get across. Assume n divides I minus j. What does that mean? Go back to chapter 0. What does it mean for one number to divide another number? Don't get confused by this notation. This doesn't mean n divided by I minus j. N divides I minus j. In other words, n is a factor of I minus j. I minus j, in all likelihood, is, if it's positive, at least is bigger than n. It means there exists a k in the integers such that I minus j equals n times k. When you divide I minus j by n, you get a remainder of 0. Now we got to tease out what that means. Why does that mean this is true? Again, we got to still use the fact that the order of a is equal to n. That must be relevant somehow. Takes maybe a little bit of experimentation. Certainly a to the nk, we got to get n involved, is a to the n to the k, property of exponents. This is similar to what we just did a few minutes ago. That's e to the k, which is e. And by what we're assuming here, that n divides I minus j, so that this is true, that's also equal to a to the I minus j. So the assumption here that n divides I minus j, leading this equation, leads to the equality between these two things. What we're trying to show is that a to the I equals a to the j. How do you do that? Well, you can use property of exponents. You can write this as a to the I times a to the negative j. And then you could multiply both sides of this equality by a to the j. Do it to one side, do it to the other. And then use property of exponents again. That's going to simplify to a to the I minus j plus j equals a to the j. J and negative j cancel. You're left with a to the I equals a to the j. I could definitely see putting a proof like this on exam 1. This level, maybe even this proof. The other direction is a bit harder. Maybe too hard to put on the exam unless I gave you a hint, some guidance, or maybe I'd fill it in the proof and you'd have to fill in the blanks for reasons. Assume a to the I equals a to the j, and try to show n divides I minus j. Again, we're assuming the order of a is n. The fact that a to the I equals a to the j does mean we could reverse the steps that we just did in the previous part and say a to the I minus j does equal the identity. Maybe that's useful. If I wanted to show a step to get from here to here, I could multiply both sides by 8 of the negative j and use properties of exponents. Trying to show n divides I minus j. What's the key? Try the division algorithm again. If we could apply the division algorithm to I minus j divided by n effectively and get a remainder of 0, that would be enough to say n divides I minus j. At the start, the division algorithm is going to say there exists unique integers q and r in Z such that we're again dividing I minus j by n. It's a little bit strange, but we can do that. I minus j is certainly an integer. And again, the uniqueness is with respect to the condition that r is between 0 and what we're dividing by, or which is the n, possibly equal to 0, but not equal to n. Again, what's our goal? Our goal is to show that n divides I minus j. It'll be good enough to do that to show r equals 0. We don't know at the start here that r equals 0. We want to show that. Must be related to this fact, or the original fact. Do a little experimentation. Okay, what would this equality imply? And this one, if I combine them. E equals a to the I minus j, I could replace I minus j with Qn plus r. My goal is to show r is 0. Is it possible I could do that from this fact? And maybe it's almost always important that r is between 0 and what we're dividing by. 0 and n, possibly equal to 0, but not equal to n. I hope it makes most sense to just try simplifying this. Try using properties of exponents again. Oh, and use the, okay, I haven't used the fact. Well, I haven't used the fact that A has order n yet. Use that, just like we did before. What does it imply? It implies that all this simplifies down to a to the r. We've done this kind of calculation a number of times already. It's still relevant. So what do we have here? We have the identity equals a to the r. Now think. The order of a being n doesn't just mean a to the n equals e. It means more than that. What else does it mean to say the order of a equals n? For example, the order of a being 6 doesn't just mean that a to the 6th equals e. A to the 12th would equal e, a to the 18th would equal e, yep. But it also means more than that. It also means, for example, a to the 5th does not equal e. A to the 4th doesn't, a to the 3rd doesn't. 6 is the smallest positive power, getting you back to the identity. Same kind of thing here in the abstract. When I say the order of a equals n, yes, a to the n equals e, but just as important, n is the smallest positive power, bringing you back to e. R is smaller than n. And we're saying a to the r equals e. The only way that can happen then, since r is smaller than n and n is the order of a, is that r must be 0. Therefore, r equals 0 since n is the smallest positive power of a. bringing you back to E. And R is smaller than N. The only way that's going to happen is if R is 0. Positive does not include 0. Positive numbers don't include 0. N is the smallest positive power. It's not 0, it's 1 or 2 or 3, etc. Bringing you back to E. R is 0. A to the 0 power is E. And yes, since R is between 0 and N, not equal to N, this equality must mean R must be 0. And that does it. If R is 0, then I minus j is q times N. In other words, N divides I minus j. Therefore, I minus j equals q times N, so N divides I minus j. Let's study the proof of this theorem right here without writing things out, but let's just point some key things out and help you come to the point where you believe you could prove this or parts of it, maybe with some help. Let A be an element of order n in a group. Some group G, the group G is again not necessarily cyclic. Any group does have cyclic subgroups. Cyclic subgroups generated by elements. The entire group might not be cyclic, but it's got plenty of cyclic subgroups. Let K be a positive integer. Then the cyclic subgroup generated by K is the same as the cyclic subgroup generated by A to the K is the same as the cyclic subgroup generated by A to the GCD of N and K. Kind of confusing looking at this equation. If you think about examples, it definitely helps a lot. I won't take the time here, but you should, if you haven't done so yet outside of class. And the order of A to the K turns out to be N divided by the GCD. You know, and a good example might be to take N to be, say, 40 and K to be maybe 15 or something like that. If N is 40 and K is 15, we're trying to figure out what's another way to write the cyclic subgroup generated by A to the 15th. It'd be the same as the cyclic subgroup generated by A to the 5th. Why? Because 5 is the GCD of 15 and 40. And the order of A to the 15th would be 40 divided by 5, 8. It's pretty easy to see that A to the 5th would have order 8. It's also true that A to the 15th would have order 8. It's just one example. It's worth writing down and thinking about other examples. Well, let's study this proof. First, to simplify notation, let G be the GCD of N and K. Okay, so just keep that in your mind. As you read, D is assumed to be the GCD. Let K be D times R. Why can you say that? Always ask yourself that kind of question. Why can we say the next step is true? K is an arbitrary positive integer, N is another arbitrary positive integer. That's the order of the element A. D is the GCD of N and K. Oh, so it is a divisor of K. If I take K and divide by D, I'll get a remainder of 0. I can write this. K equals D times R. D divides K. Since A to the K equals that, that's a property of exponents, and just using that last equation, we have by closure that this is true. Okay, that's probably the first kind of challenging thing to think about there. The author is claiming this inclusion, this set is a subset of that, follows from this fact right there. Why? Always ask yourself why. Well, in this case, you have to ask, what does it mean to be in these sets? That notation means the set of all powers of the A to the K. This means the set of all powers of A to the D. So to say this is true means, think about it with me, every power of A to the K must be a power of A to the D. In particular, why did this say closure? A to the K itself must be a power of a to the d. Well, that's exactly what that equation says. A to the k is a power of a to the d. So a to the k for sure is in there, is also in there. Why does he say by closure? Because now every power of a to the k, which by closure will be in here, will also be in here, because this is a subgroup. It's closed. Say that again. Why is closure invoked? We know a to the k is in here, and we've just shown it's in here. It's really the closure of the subgroup on the right. That's a subgroup. It's closed under multiplication. In particular, since a to the k is in it, any power of a to the k is in it. And that's why this is a subset of that, because this by definition is all powers of a to the k. All right? Tough to think about this early in the morning. We'll talk about this. You get it for 2 seconds and all of a sudden it's gone. You have to rethink about it. You have to have some coffee if necessary, or some pop if you prefer, or something. By theorem 0.2, the GCD theorem. That means the GCD is linear combination theorem. So this is the next thing we're trying to do. We're trying to prove this inclusion there. We know there exist integers s and t, so that the GCD is the linear combination of n and k. D is the GCD of n and k. So this has got to be true for some integers s and t. Use that fact. It's really powerful. We're trying to show that inclusion there. Effectively, by closure, we're trying to show a to the d is a power of a to the k. A to the d, blah, blah, blah. Use GCD's linear combination theorem. Use properties of exponents here and here and here. Use the fact that a has order n right there. Don't forget about that. To simplify to this, which is a power of a to the k. We have proved a to the d is a power of a to the k. It's an element of the cyclic subgroup generated by a to the k. And therefore, any power of a to the d is also in the cyclic subgroup generated by a to the k by closure of this. Both inclusions imply equality. And the GCD there, that's D. Okay, I think I'll stop at that half of the theorem. You can wrestle with the second half. I could see putting this first half partially on the test. Maybe not both inclusions, but one inclusion. Then maybe I give you the hint to use the GCD's linear combination theorem. Maybe that would be your goal on the problem on the test, is to verify that. Okay, so this is definitely worth wrestling with.